Hi, we're Team 23090, Autonomous Robotic Race Car. We are sponsored by Tucson Embedded Systems, and this is our Design Day video. We're going to be quickly introducing ourselves, starting from the left of this picture.
Hello, my name is Ezra De Pineda. I'm a mechanical engineer.
I'm Ryan Prather, an electrical and computer engineer.
I'm Nicolas Cornejo Lopez. I'm electrical and computer engineer and also a procurement lead.
I'm Leon Farhaj. I'm an engineering management student and the team lead.
I'm Malcolm Neifeld. I'm a mechanical engineer.
So to give an intro to our project, there's two main goals. First, we want to build two high-speed autonomous 1/10 scale race cars. There's been past work done with this with existing organizations like F110 and also from our sponsor. So then we have additional goals on top of that, which is our second one. But with the idea of two, we first want to have a car that verifies individual components and their overall function. And then using that findings, we'll have a development of our second car that improves on it. The idea of the autonomous components, with our second goal is that we want it all to be housed in one package so that we can make it modular and hot swappable. This is our largest external merit of our project and what we're building on from past work. And we named this our race module for movable autonomous control electronics. Here's a design day poster which gives some of the previews into what we're going to be talking about. You can see on the top we have our first car, on the left we have our second, and then we also have different iterations of our race module. Before getting into more detail, it's important to know standards. Just want to make sure that we're being aware of all the safety considerations that we have. For us specifically, there's things like individual components, lab usage, electronics testing. With these, there's mainly ISO and IEEE standards, as well as the Machinery Use Handbook. So for our actual project, here's our system block diagram. We started with a base RC car known as a Traxxas, we'll see at the top left. And on that, we have our race module. So again, all of our autonomous electronics. That also has software on it, and then we have a custom track that we made, and also an external command computer that works with our race. Diving a little bit deeper into our race, you're going to see there's an electronic speed controller, a buck boost converter, a LiDAR sensor, computing module, and a Wi-Fi antenna. This is all interfaced with the battery, and then again, the custom codes track, and then on the base Traxxas vehicle, and also an external command computer.
Now moving on to our system requirements. We have four. We have performance, software, environment, and interface. However, our sponsor wanted us to focus more on performance.
I'm going to discuss trade studies, one of many. One of the things we looked at was how to mount the components to the race. As you can see, we have three options, and we chose to use screws. Next, we did a trade study on the track, and we tested different track wall materials, as well as brackets that we would use to hold that track wall up. And I'm going to discuss the differences between the two cars. So our second car gets a significant boost in computing power from our first. Our second car has the Jetson Xavier NX. Our first had a Raspberry Pi 4. Both require different powers, so we had to use different power boards for each. And lastly, we 3D printed a race instead of laser cut Delrin. The second option gives us more complexity and flexibility in design and meets our goal of making the sub-chassis swappable. And as you can see here, we have a side-by-side comparison. On the left is our first car with that Delrin cut sheet. On the right is our second car with 3D printed race.
Here we have the original design for our Delrin cut plate. We laid out each component because it allowed easy access between the components themselves so they can be connected simply, as well as easy access to the lower car itself so everything can reach the components that need to, such as the motor. This is the second design for our race chassis. We dropped it down to try to decrease the form factor, but still had a number of design requirements that we were not meeting for our second car, so we moved on to our third race design. Which we can see here. We put our LiDAR on a platform above to ensure an unobstructed view. Additionally, we have added some holes in our step downs to allow for airflow. This helps with cooling of each component, as well as walls around the whole race. This helps in case of a turnover for protecting each component. Additionally, all the components have more room between them now, so they can be more easily connected together and more easily access all components on the car itself down below. Here we have a video of our car running the track. This is just a loop track that we built in the TES warehouse to test the car's autonomous software. We were able to run the car both directions on the track and saw it drive successfully. And we have now designed a new track, which we are testing, as we will see in the next slide. So here are my teammates setting up the new track. This track has both straightaways as well as left and right turns and very sharp turns to test all kinds of driving that our autonomous software will need to be able to perform.
Moving on to the verification table for performance. As you can see, these are all passes. We were able to navigate at 5.8 miles per hour on average around our custom track, all while carrying a 2.2 pound load, which is approximately what the race module weighs. And the car was able to turn at speed as well as slow itself down if needed. And battery was able to last longer than 30 minutes. For software, the LiDAR was able to transmit at least 8 data points per scan, and the software was able to process all of that for use in the ROS software, as well as the ROS software was able to have a working simulation of the car and display current track conditions in the form of a map. However, we did fail for route determination. The Raspberry Pi was not able to handle that algorithm, and our sponsor told us that this was not intended to be a software-intensive project, so we went away with route determination. For environment, track turns and track wall height, the track has both left and right turns that the car is able to navigate through, and the cardboard we used for the track walls is exactly 2 feet tall. And then in terms of weather conditions and track conditions, the car was able to drive autonomously indoors and outdoors on polished concrete as well as on asphalt. For interface, this mostly relates to how everything is connected together. So we used standard M3 screws to secure most of the parts and standard USB connectors for data and power. And then the car was able to connect to the external computer via Wi-Fi, and the power board was able to supply safe power to all components that needed it.
And last, we have our lessons learned. First one being importance of prototyping. We learned this because we had our first car, which is our prototype, I guess. And then we also had our second car, which was we worked on our prototype to make it better. Second, we have tolerances related to 3D printing. We had an issue here because when we 3D printed, some of the mounting holes were not lined up correctly. And so going forward, we definitely want to make sure that we get those mounting holes lined up correctly. Another thing we had was planning and scheduling. A good way to combat this would be implementing Scrum. Next thing was more rigorous testing throughout. We did a lot of our testing towards the end. However, this could have saved us more time and stress if we did it throughout the project. Next was making smart design decisions. This could be done through discussing with the team and trade studies to make sure we have the best car possible. And lastly, we have planning for overall system integration. One of our issues that we had was the fact that when we made our race module, a race chassis, our electronic components would not always fit. And so that was kind of an integration problem. And going forward, we want to make sure that all these considerations are done before we print it to make sure that we don't have to waste time printing more chassis. And lastly, we have acknowledgements. First of all, I'd like to acknowledge Tucson Bend System for a sponsor, starting with John Schwab, Logan Bank, and Roger Gibson. Then our professor, Dr. Elmer Grubbs. And lastly, the senior design capstone team, Larry Head, Debbie Claggett. Thank you for listening to our presentation.